To start lecture B, I want to show you some stuff on Mathematica related to what we just did in lecture A. So here was the function for the minimum cost problem. Remind yourself of some things I told you already as you look at this. When you first define the function, you need underscores, not just for the v in this case, but also for the a and the b. I'm making those as subscripts in Mathematica, more for myself, just to remind myself that those are the parameters. But Mathematica treats them as variables, so they still need underscores. And there's the formula. So you enter this formula. The semicolon, by the way, just suppresses the output, though that's not a real big deal there, because we're going to see it anyway. Here's its derivative. Here's what you would type to solve for the critical point. Again, remember to make sure you use two equal signs, not one. It's going to mess it up if you just use one. Okay? It's going to store stuff in memory. It'll mess up your later calculations. Always use two equal signs there. Which one of these three is the one we want? It's the one that's simplest. It's the one in the middle here. That is how the critical point depends on A and B. You might remember there was a cube root of 500 in mine. That is the same as 5 times 2 to the 2/3 power. That's the same as the cube root of 500. The second derivative can be found as well. That's positive for all v positive, because A and B are automatically positive as well. And here I can plug in the critical point into the original function to find the minimum cost. And here's this formula. And I could make a manipulate of the plot. Let's quickly do that, remind you how to do that. It's always easiest in Mathematica to work sort of from inside out. Make your basic plots first, for example, and then put them inside and manipulate, because that'll avoid errors. So, basic plot can be found just by plotting the function. I can use the subscript button over here. I can go f sub a comma b. I no longer need underscores. V goes from, say, 0 to 50 or something. These are speeds in miles per hour. If I plot it as it is, it won't do anything because I haven't told it what A and B are. If I plugged in something specific for A and B, like 100 and 675, then I get a specific graph. You'll notice the lower left corner there is not the origin. Sometimes Mathematica does that because it just looks better, but I like putting the origin at where it should be. I can add this option, axes origin, capital A, capital O, arrow, 0, 0, and it forces the lower left intersection there to be at the origin. It'll also change the plot range a bit. And it looks like for your problem on the assignment, the minimum speed is somewhere in the ballpark of 14 or 15 or 16 miles per hour. And the minimum cost is around $70-something per hour, right? No, dollars per mile. Okay? Dollars per mile. But now I can put this in a manipulate and change A and B. This kind of syntax will start A off at 100, let it go lower if I want, and let it go higher. This kind of syntax will start B at 675, let it go lower or higher. As this is, it'll adjust the plot range. Maybe you like that, maybe you don't. I need to change these to A's and B's. If nothing changes, that's the kind of mistake you might have made. As it is, it changes the plot range as I move these. If I want to keep that fixed, I can add an option inside the plot, comma plot range. 0 to 50 would be the x direction, and say 0 to 1,000 or something like that for the vertical direction. I guess these axes would be V for the horizontal and C for the vertical. Now I've fixed those and I can make the changes, and that's probably a better way to look at it. You can see the qualitative effect of these changes. And those partial derivatives we calculated in the sensitivity analysis quantify the changes in both the low point, both its V coordinate and its C coordinate. Those partial derivatives quantify those changes. Okay? I won't get into more detail. Let's also look at the slope field. Well, okay, let me show you one more thing in this part. Again, D will calculate derivatives, and if I got two variables, it's probably better to use d instead of prime. This first thing will calculate a derivative with respect to a of the critical point. And then percent sign in Mathematica always refers to the preceding output. So whenever you use it, it's always a little tricky. You always have to have entered that preceding output. And this syntax will then just plug in the numbers a equals 100 and b equals 675. Don't worry why it works that way. That's just the way to do it. There's where I got the negative 0.05 for that one partial derivative that we looked at on one of those slides from lecture A. Down here, let's look at the slope field for this. DSolveValue, by the way, will find a formula for the solution. So the equation, the differential equation was dy dx equals f of xy, which is 2x minus y. That's the syntax for using DSolveValue to get your solution. I need a y prime of x there equals f of xy. I need to replace y with the function y of x, because Mathematica needs to know that's a function of x. There's an arbitrary initial condition. I could have picked something specific. And doing expand at the end will make the function look nicer. There's a solution. And this syntax, I'm not going to explain. It will plot both the slope field and the solution in the same picture here. And in fact, I've allowed myself to change the initial condition. To manipulate where the initial value of y can change, and you can see the different graphs, but all of them do follow the slope field, no matter what the initial condition is. Okay. All right. The remaining tasks here in lecture B are to look at second order differential equations, which have applications mostly in physics, because of Newton's second law, F equals ma, that's the reason. And then we'll also do a couple more related rates problems. So what is a second order differential equation? On this slide, I don't have any equations, I just have descriptions, brief descriptions. I will put examples on the board. Differential equations can also be second order, not first order. First order is the ones we've been talking about so far with slope fields. dy dx equals f of xy. It's called first order because it only involves a first derivative. Second order equations involve second derivatives, which could be accelerations in physics. Typically are accelerations. And therefore, F equals ma, Newton's second law, is a common situation where second order differential equations arise. Here are the most common examples. Free fall, which we've already talked about back, it was 3 or 4 weeks ago we were talking about free fall before exam 2. In these physics applications, typically time is the independent variable, t, instead of x. So for this example 1, if height is the dependent variable, here is a second order differential equation. And it does come from F equals ma. F equals ma in the free fall situation implies what? Well, the force is going to be negative mg. When g is the acceleration due to gravity near the surface of the Earth, that's got to equal ma. The m's cancel, leaving you with an acceleration that's constant, negative g, which is about negative 9.8 meters per second squared. This equation right here is exactly this equation right here. They're the same thing, because acceleration is the second derivative of height. So that's a second order differential equation. How did we solve this back 3 or 4 weeks ago? We integrated. We talked about antiderivatives. V, which is the first derivative of h with respect to t, is the integral of negative g. And we found that was negative gt plus the initial velocity. Certainly any function like this has a derivative equal to negative g. T is the variable. It also has an initial velocity of v0, because if you plug in t equals 0, you get 0 then. and then integrate again to find the height. And we've got negative 1/2 gt squared plus the initial velocity times t plus the initial height. So we solve that differential equation by integrating. Example 2, what if we added air resistance to this? How would it affect things? Put that over here. Try to make it big for you guys over on the left here. If we added air resistance in this F equals ma equation, Newton's second law, it affects the force. It doesn't affect this side. It affects the force side. You've got two forces going on. You've got the force due to gravity, but then you also have air resistance. The force due to gravity is still the same, negative mg. G is the acceleration due to gravity. Mg without a minus sign is the size of the force due to gravity. The negative sign just means it's pointing downward. But what about air resistance? Well, different situations call for different models of air resistance. It depends on whether the object is a rock or a feather or somebody skydiving. It also, I mean, if you're skydiving, it depends on if you're like spread eagle or if you're trying to actually dive straight down or something, right? That affects how fast you fall because it affects your air resistance. By the way, I do want to go skydiving someday. I have not yet, but maybe next year or the year after. If I do, I'll post it on Twitter. You can follow me on Twitter, by the way. I'll post it on Twitter, my skydiving, if I do. What about that force due to air resistance? It turns out to oppose the velocity, okay, with a negative sign. Maybe not some constant negative k times the velocity. If you're going downward, if v is negative because you're falling, then this is actually pointing upward, it's positive. Okay, that force would be upward. On the other hand, if you're going up already, if you are shot out of a cannon going upward, then your velocity is positive and this force would be negative, it points down. It always points the opposite direction of the velocity. This needs to equal ma. This is a differential equation. It can be written as negative mg minus k times the derivative of h with respect to t plus equals m times the second derivative of h with respect to t. It's a more complicated differential equation. It's definitely harder to solve. You can't really solve it, it seems, just by doing something like this. Or that might not be clear. We will talk about how to solve this, I think. Well, that may not be best. We'll come up with a solution for this next time, but we probably won't talk about how to get the solution. That'll be too much. Okay. But that's a model for free fall with air resistance. What do the solutions look like? Give you a little hint. If this is a model of a height versus time without air resistance, then the model of height versus time with air resistance looks more like this. It doesn't look that much different, but it is a little different, and it does have different formula. But it should make sense that it should look similar. Example 3, mass on a spring, also called the harmonic oscillator, which we've talked about before with the frequency and the period. But it's a differential equation that models it. Once again, you think about F equals ma. Imagine you have an immovable wall over here and ice down here, and you're in a vacuum in here, you're trying to remove all friction. But there's still friction inside the spring. When you grab this mass and stretch the spring and let it go, it starts moving, right? It oscillates back and forth. If you pull it too far, it might hit the wall. Pretend you haven't pulled it far enough to hit the wall. Or you can push it, scrunch the spring, and then let it oscillate. But they do oscillate, so you've got some cosines and sines, perhaps, some periodic functions involved in the solution. That's why you can talk about the period frequency of the solution. If there's no friction, then the force is just the restoring force of the spring. If this is, say, the x direction here, it would actually be negative some constant times x equals the mass times the second derivative of x with respect to theta. I'm thinking of x horizontal as being the dependent variable here. Solutions of this is a second order equation, do involve trig functions, cosine and sine. And that should make some intuitive sense. For example, if you take m and k to both be 1, then your differential equation simplifies to this. And what that means is you're looking for a function whose second derivative is the opposite of the original function. Cosine and sine have that property. The second derivative of cosine of t is negative cosine of t. And the second derivative of sine of t is negative sine of t. They have the property that the second derivative is equal to the opposite of themselves. Somehow the concavity is given by the output in a way, though that's harder to interpret than the slope being given by the output. Okay, just wanted to introduce that today. We'll get into it more in coming days. To end class today, we're going to do a couple more related rate problems. Have some similar problems to these in your assignment. Here's kind of a classical type of problem. A ladder leaning against a wall and sliding away, which you don't want to have happen, right, if you're standing on the ladder. That would be bad. It's a very slippery floor. An 8-meter ladder leans against a vertical wall, and the bottom of the ladder slides away from the wall at a rate of 0.75 meters per second. Meters back to straight, say 0.75 meters per second. 1,001, maybe something about that fast. It's sliding away from the wall. At least at a certain instant in time. It might speed up. How fast is the ladder sliding down the wall when the bottom of the ladder is 2 meters away or 4 meters away? You need to draw a picture of the general situation. There's your wall. Over here. Here's your ladder. Hey, I see a right triangle. Either the Pythagorean theorem or trigonometry must be relevant. They both technically apply, but maybe we would only use one of them. Let's call this distance x and this distance y. The hypotenuse is constant, right? That's the ladder. That's 8 meters. But x and y are changing. The ladder is sliding away from the wall. X is increasing. Now, that's maybe a little confusing because usually we think of leftward motion as negative direction. Maybe it would have been better to draw it this way. But I am thinking of x as a positive quantity here, not negative. It doesn't matter if you draw it that way. The ladder is sliding away from the wall, x is still increasing. dx dt is still positive. That's the positive 0.75 effect. We want to find how fast it's sliding down the wall. Find dy dt, which will necessarily be a negative quantity, right? Because y is this distance, and as it slides down, y is decreasing. When dx dt is positive 0.75 meters per second, and two conditions, either A, we are 2 meters away from the wall, x is 2 meters, or B, x is 4 meters. So x and y are both functions of time. It doesn't matter that I don't know what functions of time. It doesn't matter. In fact, that's not the goal of the problem. It would be for differential equations to figure out the functions in that. but not for related rates. The Pythagorean theorem implies that x squared plus y squared equals 8 squared, 64, no matter what x and y are in this situation. No matter what time we're at. Even though x and y are changing. In a sense, this is kind of a constraint. X and y are functions of time, but they must always satisfy this equation. If I call x f of t and y g of t, I could rewrite that equation as f of t quantity squared plus g of t quantity squared. That would be okay. That would be okay to do, actually. And I can write my derivatives in terms of primes of those functions. That might be an easier way to go, just like it was with implicit differentiation for some people. It's just not traditional to do that. It's more traditional to use the Leibniz notation for the derivative here. Differentiate everything with respect to t. Both x and y depend on t. In both cases, I do not get 0. I get 2 times the function times the derivative of the function by the chain rule. 64 is an honest-to-goodness constant. Its derivative is 0. If I was using this notation here, I would write it as 2 f of t times f prime of t plus 2 g of t times g prime of t equals 0. That would be okay as well. Either way is okay, and perhaps this method is less confusing, but that's more traditional. What do we want to know? We want to know dy dt. Just solve that equation for dy dt now. You can cancel the 2's. You can write y dy dt equals negative x dx dt. Right? Just subtract x times dx dt from both sides. And I canceled the 2's. Essentially, I just divided everything by 2. Now divide everything by y. dy dt equals negative x over y dx dt. It's kind of confusing because you only see the t's in the dt parts here. But x and y both depend on t. If I was doing it this way, trying to solve for g prime of t, the answer would be g prime of t equals negative x over y, which would be negative f of t over g of t times f prime of t. That would be fine to do it that way. And that's really, again, less confusing. This is what it really means when I write this. Everything does depend on that. Now you plug the numbers in. The FTT is 0.75. We do need to use the Pythagorean theorem again to solve for y algebraically when x is either 2 meters or 4 meters. If x is 2, then we get 4 plus y squared equals 64. So y is the square root of 60. Square root of 60 is the same as square root of 4 times square root of 15, 2 times square root of 15. But I am fine just leaving it as square root of 60. When x is 4, I get 16 plus y squared equals 64. Y squared then would be 48, and y would be square root of 48. That's square root of 16 times square root of 3. That's 4 root 3. So finally, to answer the question, when x equals 2, what is dy dt? Plug all the numbers into this equation. Plug in x is 2, y is square root of 60, and dx dt is 0.75. Negative 2 over square root of 60 times 0.75, whatever that turns out to be. And this is 3/4, you could write it as a fraction instead of a decimal. You know, it's going to be a fairly small number, less than 1, with a negative sign, because y is decreasing. I won't take the time to figure it out. When x is 4, dy dt would be, use the same formula, now x is 4, negative 4 over y is going to be square root of 48. Dx dt is still 0.75. That's going to be bigger. When the ladder's further away, the bottom is further away from the wall, y is going down faster. It's a bigger negative number, so to speak. That's what I meant to say. One more problem. A ruptured oil tanker causes a circular oil slick on the surface of the ocean. When its radius is 100 meters, the radius of the slick is expanding at a certain rate. And it's got a certain thickness. Part A, how fast is the area expanding? Part B, the circular slick has to be the same thickness everywhere. It doesn't seem like it's necessarily realistic, but that's what it said there in the book. Just modify the numbers from the book. And its volume remains the same because it's still the same amount of oil, saying that's completely still. How fast is the thickness decreasing? So it seems to me, based on how this is phrased, that we're modeling the oil spill as like a thin cylinder, a thin hockey puck. Let's call its thickness h for height. Let's call its radius r. Part A is about the area of the slick. If you're looking straight down on it and looking at that area without thinking about the thickness, it's going to look like a disk, a circle. Its area is going to be pi r squared. How fast is the area expanding? We need to differentiate it with respect to time. All these quantities, r, h, and a, all depend on time. R is a function of time. When I differentiate this with respect to time, I need to bring the 2 down, subtract 1 from the exponent, then use the chain rule again. This is always the chain rule right there. That's the derivative of the inside function. So to finish part A, we would need to know the area when its radius is 100. Plug in r equals 100, plug in A. Well, I guess we don't need to know A. We just need to know r and the RDT. R would be 100, and the RDT would be 0.2 meters per minute. You always want to make sure you do the derivative first before you plug the numbers in. Don't plug the numbers in too early. This, in exact form, would be 40 pi. It's an area, square meters per minute. And 40 pi would be in the ballpark of 120 something. In part B, we're essentially pretending all the oil has come out. So it's got a fixed volume. It does keep expanding, but because it's the same amount of oil, that means the thickness has to be shrinking. If it's truly going to be like a thin cylinder in shape. And again, don't worry about whether that's realistic or not, we're just trying to solve the problem. How fast is the thickness of the slick decreasing? The volume is 4/3, excuse me, that's a sphere. The volume of a cylinder is pi r squared times h. That's supposed to be a constant. So now when I differentiate with respect to t here, I differentiate the right side, I do get 0. And here, both r and h depend on t. The slick is expanding, r is increasing, but it's getting thinner, h is decreasing. They're both functions of t. I need the product rule. I've got a first function, say pi r squared, and a second function, h. Lefty right plus righty left. Left dv dt, which by the way will be 0. This is constant. V is constant. Will be left. D right, the derivative of h with respect to t is just dh dt. Plus, that's lefty right, plus right d left. D left is going to be 2 pi r dr dt. And then times h, that's left. That's right d left. That equals 0. What should you do now to finish the problem? You want to know how fast the thickness is decreasing. That's dh dt. You want to solve this equation for dh dt in terms of r and h and dr dt. You then plug in r equals 100. The dr dt is 0.2 meters per minute, and h is 0.01 to finish it. You should get a negative derivative because h is getting smaller. However, the problem in this phrase is how fast is it decreasing? You want to take the absolute value of that to get a positive final answer. Make sense? All right, see you Wednesday.